Welcome to today's lesson on heat stoichiometry. Today we're going to take what we've learned about the heat of a reaction and what we already know about stoichiometry and combine the two concepts. So hopefully you will see some usefulness to the delta H of reaction calculations that we've done in the past two lessons. So let's start off with the delta H of a reaction, just a quick review, that it is the energy lost or gained during a reaction. And we're going to use the concept that the delta H of a reaction and the balanced equation allow for converting between mass and heat for a given reaction. And the reason that we can do this is because the units for delta H of reaction are equal to kilojoules per mole of reaction. And that gives us a conversion factor between moles of the reaction and energy. And then we can use the coefficients in the balanced equation to tell us our mole ratios. The easiest way to see how simple this process actually is through an example. So in this example, we have the reaction between iron and oxygen forming iron oxide. And we're given this delta H of reaction is equal to negative 1652 kilojoules. But as we know from before, from one of the previous slides, that's actually kilojoules per mole of reaction. So whether that per mole of reaction is written or not, it is implied, and it is actually that you need to consider that it's actually there. So question of how much heat is released when 223.4 grams of iron react? Well, just like in previous stoichiometry problems, we're going to start out by underlining our given of 223.4 grams of iron and boxing what we're looking for. So we're looking for heat. So we're in a box, put the heat into a box. Okay, so just like all stoichiometry, you start out with your given. So we're going to write down our given of 223.4 grams of iron, and we're going to follow it with a times sign and a line. We want grams of iron on the top, and because we need to change units, we know we need to go through the moles, so we're going to go to moles of iron. And we know that 1 mole of iron weighs 55.85 grams from the periodic table, and then grams of iron cancels out, and we are currently in moles of iron. Well, we need to get to moles of reaction. So we're going to go moles of iron on the bottom to get rid of it. And on the top, we're going to have moles of reaction so that we can transfer that to heat using our delta H. So for every one reaction, we have 4 iron that are used. So moles of iron now cancels out, and we have moles of reaction. This then allows us to go from moles of reaction to kilojoules using our delta H of reaction. And so for every 1 mole of reaction, we have 1,652 kilojoules. And the reason I didn't put the negative sign here is because it already tells us that the heat is being released, which is the same thing that the negative sign tells us, so it's redundant to put it in there. If it said how much heat is associated with 223.4 grams of iron reacting, then you would need to include the negative sign because it's not telling you whether that heat is being released or absorbed, and that's what the negative sign indicates. So we have moles of reaction, and we're left with kilojoules, which is what we wanted to know about because heat is measured in kilojoules. So we take our 223.4 grams times 1 mole times 1 mole times 1,652 kilojoules, divided by 55.85, divided by 4, and we should come up with 1,652 kilojoules. And we're going to move on to another example. We're using the same reaction again, so again we have to add in the per mole of reaction. And this time we're asked what mass of O2 is used if 397 kilojoules is produced. So we're given the 397 kilojoules, And this, now we're asking for mass of O2, which is in grams. So we measure mass in grams. So we start with our given just like before. So we start with 397 kilojoules, and we want to get rid of kilojoules, so we're going to put that on the bottom. And in order to get to O2, we need to get to moles of reaction first. So we know that that's 1,652 kilojoules per 1 mole of reaction, and our kilojoules will cancel out. And then we're going to go from moles of reaction to moles of O2. So our moles of reaction will end up canceling out. But for every 1 mole of reaction, we have 3 moles of O2. And now the last part is just a simple mole to gram conversion. So we have moles of O2 on the bottom, and now we need to go to grams of O2, and we know that 1 mole of O2 is 32 grams of O2. And so we take the 397 times 1 times 3 times 32 divided by the 1,652 kilojoules, and we should end up with 23.1 grams of O2. Our moles of O2 there cancels as well. And we have one last example that's a little bit more challenging. Not much, using the same processes that we've done, but it got to jog our memory of one more concept. And that is, so how much heat is released when 10 grams of iron and 2 grams of O2 react? So our given, well, we have 10 grams of iron and 2 grams of O2, and we're looking for heat. We know that heat is in kilojoules. Well, this time I underlined 2 things. That means that there's 2 givens. If you remember back to stoichiometry, when there's 2 givens, that means that we have a limiting reactant problem. So that means we have 2 calculations. So we're going to start with, we have to convert each of these to kilojoules and see which one produces the least amount of heat. And that's going to be the amount of heat that we actually have. So start out with 10 grams of iron. And again, we're going to convert that to moles. So there are 55.85 grams per 1 mole of Fe. And then we know that there are 4 moles of Fe per 1 mole of reaction. And then again, we're going to use our delta H as a conversion factor, and that 1 mole of reaction, it produces 1,652 kilojoules. And when we do that, we get 73.9 kilojoules of energy released. But we're not done because we still have that other conversion to do, and that is 2.00 grams of O2. And we're going to convert that to heat as well. So we got to go 32 grams of O2 per 1 mole. And we know that there are, in every 1 mole of reaction, there are 3 moles of O2. And then again we use our delta H, so 1,652 kilojoules in 1 mole of reaction, and that will give us 34.4 kilojoules. So now what that means is that oxygen, because it made less energy, is my limiting reactant. So oxygen will run out before we can actually make 73.9 kilojoules, which means that we only have enough oxygen to make 34.4 kilojoules of energy. So therefore, the 34.4 kilojoules is our answer. Hopefully you found that the adding of the delta H of reaction as a conversion factor was not too difficult, and this served as a good reminder of your stoichiometry.